Assalamualaikum dan salam sejahtera. Nama saya Muhammad HAZIQ bin AULI, nombor metrik DB240184. My friend is AZFAR and Faiz Roslan. This video for presentation our group project, and the title is Continuity and Discontinuity. Concept of continuities and discontinuities in function. In calculus, continuity and discontinuity help us understand how a function behaves. A function is continuous if you can draw its graph without lifting your pencil, such as no breaks, no gaps, and no sudden jumps. When a function is continuous, small change in input, small and predictable change in output. The function is smooth, stable, and easier to study. A function is discontinuous at a point when it's not continuous at that point. Discontinuities show where the function changes suddenly or behave differently. These ideas are important for studying limit, derivative, equation, and many real-world applications. So, I will continue define continuity and discontinuity. Continuity is a function is continuous at a point if its graph has no break, jump, or holes. You can draw the graph without lifting your pencil. And discontinuity, a function is discontinuous at a point if it breaks, jumps, has a hole, or behave in a way that makes it not smooth at that point. So, we continue with type of discontinuity. We have four type of discontinuity. Firstly, removable discontinuity. The limit of the function as x approach the point exists, but either the function is undefined at that point or its value does not equal the limit. Graphically, this appears as a single hole in the graph and can be removed by redefining the function at that point. Second, jump discontinuity. The left hand limit and the right hand limit at a point both exist and are finite, but they are not equal to each other. This creates an abrupt jump or vertical gap in the graph. Next, infinite discontinuity. At least one of the one side limit approach positive or negative infinity. This typically occurs at a vertical asymptote. And lastly, oscillating discontinuity. The function oscillates wildly as it approaches at point, meaning the limit does not exist at all because the function value do not approach any single value. Important theorem relate to continuity. First, immediate value theorem, IVT. If a function f(x) is continuous on the interval ab, then for any value n between fa and fb, there is at least one number in ab such that fc equal to n. The theorem guarantees that a solution exists, but it does not tell us that exact value of the solution. Second, extreme value theorem, EVT. If a function is continuous on a closed interval AB, it will have an absolute maximum and absolute minimum value. This maximum and minimum value must occur at some point within the interval.
Assalamualaikum. My name is Muhammad Faiz bin Roslan, and today I want to present about the connection between limits and continuity. The connection between limits and continuity. Limits tell us what a value a function is trying to reach as x get close to a certain point. This works even if the function is not defined at a point. Continuity requires more than just the limit existing. The function's actual value at the point must be equal to the limit. So, a function is continuous at a point if the limit exists, the value of the function exists, and both values are equal. In simple words, limit is expected value and continuity is expected value matches actual value.
Assalamualaikum. My name is AZFAR bin ANUAR. My number metric is DB240197. Today, I will continue about part B, which is function analysis. We will begin with function 1, which is a rational function. The function we are analyzing is fx equal to x to the power of 2 minus 4 divided by x minus 2. As we analyze this function, the first and most crucial step is to look for discontinuities. Discontinuity occurs when the denominator becomes 0. In this case, that happens at x equal to 2. If we were to plug in x equal to 2 directly, we would get the indeterminate form 0 divided by 0. Now, the question is, what type of the discontinuity is this? Because the term causing the 0 in the denominator can also be found in the numerator, we classify this as a removable discontinuity, what is often called a hole in the graph. Let's look at the proof on the slide. This confirms our analysis. We can factor the numerator as the power of 2 minus 4 using the difference of squares formula into bracket x minus 2 bracket x plus 2. This allows us to cancel out the common factor, which is bracket x minus 2, from both the numerator and the denominator. For all x not equal to 2, our function is mathematically equivalent to the simple linear function fx equal to x plus 2. Since the function is virtually x plus 2 everywhere except at the point x equal to 2, we can calculate the limit. The limit x approach 2 of bracket x plus 2 is 2 plus 2 equal to 4. This is the key. The limit exists and equals 4, but the function value f2 does not exist. This is the formal definition of a hole. Therefore, there is a hole at the point 2 and 4. Finally, let's look at the graph on the right. Notice how the graph is a perfectly straight line consistent with the simplified function y equal to x plus 2. If you trace the line to where x equals to 2, the y value is 4. However, the specific point is missing from the function domain. The graph visually confirms our algebraic proof that this rational function behaves exactly like a line, but with a single removable discontinuity at x equal to 2. Moving on the function 2, we are now analyzing a piecewise function. These functions are defined by different rules over different interval of the domain. Our function fx is defined by two pieces. For the first one, for x value less than 0, the function follows the rule fx equal to x plus 1. For x values greater than or equal to 0, the function follows the rule fx equal to 2x plus 1. The goal here is to check for continuity at the transition point x equal to 0. For a function to be continuous at a point, three conditions must be met. The limit from the left must exist. Number 2, the limit from the right must exist. Number 3, the function value at the point must exist and be equal to the two limits. If all three values are the same, the function is continuous, meaning you can trace the graph through at point without lifting your pen. Let's look at the limit, which correspond to the graph approaching x equal to 0 from the left and the right. For the left hand limit, we use the rule for x less than 0, which is fx equal to x plus 1. Plugging in 0 gives us 0 plus 1 equal to 1. This is the value the orange line approaches as it gets close to x equal to 0. For the right hand limit, we use the rule for x more than or equal to 0, which is fs equal to 2x plus 1. Plugging in 0 gives us to bracket 0 plus 1 equal to 1. This is the value the blue line approach as it gets close to x equal to 0. Since the left hand limit is 1 equals the right hand limit 1, we know the limit exists at x equal to 0 and it equals 1. For the final check, the function actual value at 0, we must use the pieces of the function that includes the equality as more than or equal to 0. So we use fs equal to 2x plus 1. Plugging in x equal to 0 gives us f bracket 0 equal to 2 bracket 0 plus 1 equal to 1. All three values are the same. The left limit is 1, the right limit is 1, and the function value f bracket 0 is 1 because limit x 0 negative fx equal to limit x positive x 0 positive fx equal to f bracket 0. We can definitively state the function is continuous at x equal to 0. Looking at the graph, you can see the two pieces meet perfectly at the point 0 and 1, forming a smooth unbroken curve, which confirms our algebraic proof. We now move on function 3, another rational function, and this is perhaps one of the most famous examples in calculus, the reciprocal function fx equal to 1 divided by x. Just like our first function, we begin by looking for where the denominator is 0. For fx equal to 1 divided by x, the denominator is 0 at x equal to 0. But unlike the first function, we cannot factor and cancel out the problematic term in the denominator. That leads us to a much more dramatic type of break, an infinite discontinuity. An infinite discontinuity is characterized by the function's value shooting off toward positive or negative infinity as x approaches the point of discontinuity. Let's analyze about the behavior of the function as we approach x equal to 0 from both sides, which is clearly shown on the graph. From left, as x approach 0 from the left, you can see the orange curve drop sharply. The function value approach negative infinity. From right, conversely, as x approaches 0 from the right, the blue curve rise sharply. The function value approach positive infinity. Because the function approach infinity on one or both sides of x equal to 0, we conclude that the function has a vertical asymptote at x equal to 0. The vertical line is an essential barrier that the graph never crosses or touches. In summary, this function is beautifully well behaved and continuous everywhere except x equal to 0, where it has a major non-removable break, the infinite discontinuity caused by the vertical asymptote.
For the real-world application, we choose electricity bill pricing. Electricity rates change based on usage, or we can call a piecewise function. As we can look at the table, we have a rate structure for usage and price per usage. Why it is discontinuous? A sudden price jump occurs when usage crosses certain level. This creates a jump discontinuity. The behavior is price is consistent within each usage range, jumps at specific thresholds, and graph appears as step-like levels.